Imagine a world where tracking multiple people in a crowded stadium, a fast-paced sports match, or a chaotic surveillance feed doesn't rely on fragile guesswork, but on a system that understands motion, identity, and relationships across time like a human would. That's exactly what we're diving into today. UniTrack, a breakthrough in multi-object tracking, presented at ICLR 2026 by researchers from Northeastern University's Augmented Cognition Lab. But this isn't just another tracking model. It's a differentiable graph-theoretic loss function, a training objective so powerful it can be plugged into any existing MOTE system, transforming it from the inside out, without changing a single line of architecture. Let's break this down. Hash the problem, why current trackers fail. Multi-object tracking, MOTE, isn't just about detecting people. It's about following them consistently through time. But traditional methods split detection and tracking into two separate steps. First, detect objects. Then associate them across frames using heuristics like IOU or confidence scores. The result? Identity switches. When two people cross paths or one is occluded behind another, the tracker often gets confused and swaps IDs. There are three core failure modes. 1. Post-occlusion ID switches. When someone disappears behind an obstacle, the tracker loses them and reassigns their ID to someone else. 2. Temporal inconsistency. When a person changes posture or appearance, the tracker can't maintain a stable ID. 3. Cross-subject ID switches. When two people cross paths, their IDs get swapped and the error propagates. These aren't rare edge cases. They're the norm in real-world videos, crowded scenes, fast motion, complex interactions. And here's the kicker. Most existing models optimize for detection accuracy, IOU classification loss, but they don't train for identity stability. So even the best detectors fail when the real challenge begins, keeping track. Enter UniTrack, a unified graph-theoretic framework. UniTrack flips the script. Instead of modifying the network architecture, it redefines the training objective, using a differentiable graph representation to unify three critical components: detection accuracy, identity preservation, spatio-temporal consistency. It does this through a hierarchical graph structure that models the entire video sequence as a dynamic network of relationships. Each node is a detected object. Edges represent potential associations between objects across consecutive frames. But here's the magic. This graph is differentiable, meaning gradients flow back through it during training. The network learns not just where things are, but how they're connected over time. And it does so through three integrated components. 1. Flow-based loss, preserving identity through occlusion. The first component is the flow loss, which enforces identity conservation. Think of it like tracking water through a pipe. Objects can't appear or disappear out of nowhere. They must flow from one frame to the next. We model this with flow variables, F(t), representing the strength of association between object I at time t and object j at time t+1. The flow loss encourages confident, stable associations. But here's the smart part. It adapts to detection quality. If your detector is struggling, high false positives or false negatives, the loss automatically reduces its confidence in those associations. It's like saying, I'm not sure about this detection, so I won't trust the link. This is achieved through a smooth exponential term that scales the loss based on current detection performance, without breaking differentiability. Because during backpropagation, FP and FN counts are treated as constants, stop gradient. So the loss remains fully differentiable with respect to the flow variables. The result? Fewer ID switches after occlusion, because the model learns to wait for the object to reappear, rather than reassigning the ID prematurely. 2. Spatial coherence loss, preventing cross-subject ID swaps. Now when two people cross paths, how does the tracker know who's who? Enter the spatial coherence loss. This term penalizes associations between objects that are far apart in space, especially across frames. It computes the geometric distance between object I at time t and object j at time t+1, and multiplies it by a learned spatial attention weight. So if object I moves from the left side of the frame to the right, but object j stays near the center, those two shouldn't be linked. This forces the tracker to maintain local consistency. It's not just about proximity, it's about plausible motion. And crucially, this term helps prevent cross-subject ID switches, because when people cross, the spatial distance between their predicted paths increases, making the wrong association energetically unfavorable. 3. Temporal coherence loss, stabilizing identity during motion changes. The third component handles temporal inconsistency, when a person changes posture, appearance, or direction. The temporal coherence loss enforces smooth motion. It penalizes sudden velocity changes, those abrupt jumps in position that signal tracking failure. Specifically, it measures the difference between an object's velocity in frame t and frame t1, normalized by the frame rate, and weights it by the confidence in that object's continued existence, sum of outgoing flows. So if an object suddenly teleports across the frame, the loss spikes, forcing the network to learn smoother, more physically plausible trajectories. This is especially critical in fast-moving scenes, like sports or dance, where motion blur and rapid changes make tracking notoriously difficult. Adaptive weighting, let the scene teach the model. Here's where UniTrack gets even smarter. The relative importance of spatial versus temporal coherence isn't fixed. In a crowded scene, spatial consistency matters more. In a high-speed chase, temporal smoothness wins. So UniTrack introduces an adaptive weighting mechanism based on graph Laplacian analysis. The idea: the structure of the graph itself tells you what's going on. We compute the algebraic connectivity, the second smallest eigenvalue of the graph Laplacian, for both spatial and temporal subgraphs. If the spatial graph is fragmented, meaning objects are disconnected in space, then we increase the spatial weight lambda s. If the temporal graph is unstable, objects jumping around unpredictably, we boost lambda t. And crucially, these weights are recomputed at every training step, based on the current graph structure. No learned parameters. No manual tuning. It's a self-correcting feedback loop. The model learns better embeddings, right arrow the graph changes. The weights adapt, right arrow the model improves. This is dynamic scene-aware learning, without any extra complexity. Why this works: theoretical foundations. UniTrack isn't just empirical. It's mathematically grounded. The framework satisfies differentiability, local convergence under standard conditions, and flow conservation, ensuring physically plausible tracking solutions. The loss landscape is smoother, broader, and more stable, leading to better optimization. As shown in visualizations, models trained with UniTrack converge into wider basins, avoiding the sharp, fragmented minima that plague standard training. And the theoretical analysis proves that the flow conservation constraints are respected, preventing object multiplication or merging, while the graph structure ensures consistency across space and time. Real-world impact, universal performance gains. Now the proof is in the pudding. UniTrack was tested on 7 major architectures, from transformer-based models like MOTR and TrackFormer, to detection-tracking systems like FairMOT and ByteTrack, to advanced frameworks like GTR and MOTE. And in every case, consistent, significant improvements. On MOTE 17 and MOTE 20, UniTrack boosted MOTA by up to 9.7%, IDF1 by 12.3%, and reduced identity switches by over 50%, especially in occluded and crowded scenes. On SportsMOT, a dataset built for fast, complex motion, UTGTR achieved 84.5% MOTA, a 9.7% gain over the baseline. Identity switches dropped from 2,364 to 1,092, a 53.8% reduction. On DanceTrack, where dancers have similar appearances and synchronized movements, UniTrack reduced ID switches by 20%, improved IDF1 by 2.6%, and boosted HOTA by 6.5%. And the best part? Zero inference cost. The overhead is only during training, a 5% memory increase, and N2T complexity, perfectly manageable for modern GPUs. Ablation studies, what matters most? Ablation experiments confirmed the importance of each component. Remove the spatial loss. MOTA drops by 1.9%. Identity switches spike. Remove the temporal loss. MOTA increases slightly, but HOTA plummets and identity switches rise by 32%. Because MOTA rewards detection accuracy, but not consistency. Fixed weights. Worse than adaptive ones. Learned weights. Still inferior to the Laplacian-based recomputation. The data is clear. The adaptive graph-based weighting is key. Future directions. UniTrack currently focuses on single-camera tracking. But the graph structure is naturally scalable, making it a perfect foundation for multi-camera tracking, where spatial temporal reasoning across viewpoints becomes critical. And because it's a plug-and-play loss, it can be integrated into any future MOT system, making it a universal training enhancement, not just a specialized model. Final thoughts. UniTrack isn't about building a new tracker. It's about rethinking how we train them. By embedding a differentiable graph representation into the loss function, it unifies detection, identity, and motion into a single, end-to-end trainable objective. It's a paradigm shift, from optimizing for detection to optimizing for tracking. And the results speak for themselves. 53% fewer identity switches, 12% IDF1 gains, 9.7% MOTA improvements across diverse architectures and datasets. If you're working on multi-object tracking, whether in robotics, surveillance, sports analytics, or autonomous systems, UniTrack is a must-try enhancement. The code is live on GitHub. The paper is published. And the future of tracking just got a lot more intelligent. So go check it out. And if you like this breakdown, hit like, subscribe, and let me know in the comments, what's the next frontier in tracking? Until next time, keep tracking the future.